All right, so keep in mind what we're trying to do with this simulation. We're simulating a number of doctors for a number of trials. We have two options. Either the failure probability is P or P1. We want to evaluate this probability ratio. And if the ratio is bigger than a certain value, then we reject the null hypothesis and suspect that the doctor has made a mistake. Otherwise, we don't reject. Now, of course, each one of these doctors is going to have a probability ratio. So we're going to get a vector of probability ratios. The one thing I didn't mention is that instead of doing a probability ratio, what we end up doing, in fact, let me change the color here. Let's see if that works. What we end up doing here is, rather than taking a ratio, we take the logarithm. So it's a log probability ratio. Now, if you take the logarithm, then you're going to get the log of the numerator minus the log of the denominator. And this is what's typically done in this kind of application. It's not strictly speaking necessary, but I wanted to introduce this to you because it's so widely used in probability and it has theoretical interest. So rather than taking a ratio, we're going to take a difference of logarithms. All right, so let's go to the code and see how the code reflects what we want to do. All right, so here's the code. Let's ignore this statement for now. This is going to come in useful later. Now, of course, before you do any of this stuff, you're going to have to import NumPy. All right. So I asked you to construct various functions. The first one, bgenfun, was to create the Bernoulli trials. And of course, we have to create different kinds of Bernoulli trials. We have to create the case where they're all good, or where a certain number of good and a certain number of bad. By good, of course, I mean the failure probability is P. By bad, I mean failure probability is P1. So your first function should be this bgenfun, which can create trials according to your specification. So this P is the good failure probability, P1 is the bad failure probability, M is the number of doctors or number of rows in your matrix, N is the number of trials, which is the number of columns in your matrix, and K is the place where it goes bad. So we have the first K are good, and the last N minus K are bad. So if K equals 0, for instance, all of them are bad. Right. So here's kind of a comment, and you should comment your code. Commenting your code helps you think about what your code is doing, and it will also help you find errors. Right, so in order to create this matrix, you'll have to generate K trials, which are good. And so this one would be K trials with probability P. And then this would be, this would be with probability P1. The last N minus K trials would be with probability P1. So the first K trials would be with probability P. Now you can actually do this with a single statement, and do this with a single statement. Then you'll have to put them together. By putting them together, I mean concatenate. And then you want to return the total trials matrix. Okay, so look at your function bgenfun. Make sure it does that, because that's what we want to do. All right, next we want to create the numerator and denominator for our statistics. Remember, for the likelihood ratio. So this one is going to be generically compute the probability for, this would be for Bernoulli trials. For Bernoulli trials result, assuming the first K are good and the last N minus K are bad. So you're given a Bernoulli trials matrix. And by the way, I've reduced the number of arguments in these functions to eliminate those that are not necessary. So you should go through your code and streamline it, reduce the functions so that they have the right number of arguments. All right. Now, if I'm going to evaluate the log of the Bernoulli trials result, assuming the first k are good and the last n minus k are bad, I'm going to have to treat these two cases separately. I'm going to have to treat the first k trials differently from the last n minus k trials. All right, so I'm given my B matrix, my Bernoulli trials matrix, my probability 1 and k. So this is first k trials from B matrix. Whoops, sorry. From BMX. And this is going to be all rows. First k trials means first k columns. So we saw before how the log of the probability depends on the number of failures. There's a formula for that. You can look back in the notes to see what that is. But as I said, we have to treat the first k trials differently from the last n minus k trials. So out of the first k trials, you should count the number of failures in each row. That's going to give you a vector. And then you're going to use that to compute the log probability for the first k trial. That's going to be a vector. So you do that for the first k trials. Then you'll do it for the last n minus k trials. We'll do the same thing. So this is going to be all rows, and this is going to be a matrix. So I'm going to take the number of failures for the last n minus k trials and compute the log probability for the last n minus k trials. So I'm doing the same thing for the first k trials that I do for the last n minus k trials, but with a different probability. So this one is going to do. So this is using probability p. I'm sorry. This is going to be using probability p, and this is going to be using probability n minus p. I'm sorry, using probability p1. All right. Now, the actual probability would be the product of the two probabilities. But since we're doing logarithms, the product becomes the sum. So you take the sum of two log probability vectors. So that's going to give you the probability, the log probability vector for the observed Bernoulli trials under the hypothesis that the first k are good and the last n minus k are bad. Okay. Now, the null hypothesis says they're all good. So if you want to get the null hypothesis, you would put n here. Another way to get the null hypothesis would just be to put p and p in both places here, so all the failure probabilities are p. So that's one way of getting the null hypothesis. The other way is to put n here, which says, as I said, that all of the trials are conducted with probability p and not p1. All right, so that's going to be a generic way of computing log of probability, assuming that it goes bad at one point. Now, my alternative hypothesis is not that. My alternative hypothesis is that the probability changes to p1 somewhere during the trials. And by somewhere during the trials, I'm saying that it goes bad before the dth trial from the end. So this d is an extra feature that we may need later. So that's saying that during the first n minus d trials, it goes bad somewhere. And I'm going to compute the log of the probability for that eventuality. Now, how do I do that? What I want to do is I need to take the sum of the probabilities under the hypothesis that it goes bad at any one place during the sequence of trials. I mean, it could go bad at the first trial, second trial, third trial, and fourth trial. I'm going to get a probability for each of those eventualities, and I need to take the average of those probabilities because I'm not sure where during the trials the probability goes bad. So I'm going to be taking an average of probabilities. Okay. So to do that, I need my matrix of trials. I need my default failure probability, my alternative failure probability, and D. So to do the average, I'm going to take first the hypothesis that all the trials are P1. And I'm going to do the probability vector and not the log of the probability. So I'm going to take the exponent of the log probability that I obtained from B log fun. Okay. Right. Then I'm going to do, so that's the case where all of the probabilities are P1. And then I'm going to loop over the case where the change occurs from P to P1 after the first trial, after the second trial, etc., after the n minus d minus 1th trial. And I'm going to compute the probabilities under those hypotheses. And here I should say compute and take running total. I should say running total of probabilities. Because I want to take the average of those probabilities. So I compute the running total, then after the loop I'll return the average of all those probabilities. All right, so here we have our three important functions that are useful in our code. Now,